Okay, so my name is Rodrigo. I'm a PhD student in the Polytechnic School of Lausanne, and I'm advised by Viktor Kunc. And in this work, what we basically did, it has been already announced by Georg, because he was using this combinatory array logic to encode his frame conditions. And so what we did in this work was more mathematical description of what combinatory array logic gives you. And this mathematical analysis then allowed us to basically generalize the scope of properties that the fragment handles. So, and let me see if the pointer works. 1 second. No, because I have to connect it. Okay, so let me start with a bit of introduction to give some pointers for the audience that may not be familiar with what this problem is about. The first person to propose a use of theories of arrays or languages to describe and reason about arrays was McCarthy in this paper from the 60s. And it's not often emphasized, but the problem, so there's no mention of arrays in that paper. And what he was after was basically reasoning about the local state of his programs very much in the way that Georg has presented in the previous talk. Now, so this is roughly the language that McCarthy proposed, and it had two function symbols, right? First, the square brackets, they represent array reads, the angled brackets represent array write, and the equality predicate just compares two values, and the axioms there to reason are very simple. So if you take, for instance, the first two, they just say what happens when you read an array after you have written on it. So for instance, if the read index is the same as the write index, then what you recover is the updated value v. If they are different, so then you just get back what the original array contained on the read index. And the rest of the axioms are also expressing these trivialities. Now, since then, things have evolved a bit, and now the problem really is how you automate these things. So how do you, given an array formula, how do you say if it's satisfiable or not automatically? And we have verification frameworks and SMT solvers for this task. And some of them, they include tailored heuristics for arrays. But they have limitations. So to start with, the theory that McCarthy proposed was undecidable in the general case with arbitrary quantifiers alternations. And more generally, if you have some experience analyzing complexity of logical theories, what happens is that with the number of quantifier alternations, the complexity grows also quite fast. So what people do is to capture interesting properties and try to design specific fragments for them. And in this table, for instance, I would point to the 2006 paper by Bradley Mann and Sigma, because it became very influential. One of the nice properties it could handle, for instance, was you could write that your array would be sorted. Now, a second metric to evaluate these different fragments is the complexity they have. And that fragment of 2006 was also nice because you stayed in the lowest level you can be, right, which is NP. And, well, the different fragments have all sorts of complexities. So the 2016 fragment array for logic already goes into P space. Let me see. So, for instance, flat array fragment goes into non-deterministic exponential time. And there are also fragments for which we don't know the complexity, as far as I know. for instance, the logic of integer arrays. So these are two metrics to compare these fragments between them. And I would add a third criteria, which is the theoretical underpinnings, right? So the theoretical ideas that are behind that. And in fact, most of them are based, like where you see some theory, they are based on automata considerations, right? And otherwise, it has a very syntactic flavor. And so in this talk, what I want to do is take a more semantic-based approach. So what I'm going to do is to describe a model for the theory of arrays that is, as I said, based on semantic considerations. And so that will have the advantage that we will see clearly, right? How can we improve over it? And then it's also nice that it has the lowest complexity possible, which is NP, at least for its existential theory. And finally, it captures reasonably interesting properties because it generalizes combinatory array logic, which, as Georg said, is already implemented in set 3. And it adds to that cardinality constraints. OK, so the first thing, right, when one is faced with the task of designing a new array fragment is, well, what comes to mind, right, if someone tells me what an array is, right? And the intuitive idea, right, for that is, for me at least, is simply, well, here I show a grid, right? So in fact, we have several arrays, right? Each row is going to be a different array, and each column, they represent basically the components which are indexed by that set I, which people are used to, I being the natural numbers, but we keep it abstract. In particular, we don't even assume that I has a linear order on it, even if the picture somehow suggests it. And so from this intuitive model, the next natural question to ask is, what mathematical model captures it, right? And the answer, or at least the answer we give in the paper, is basically tuples, okay? So tuples are a well-known mathematical notion, of course, and if you have a set of tuples, you call it Cartesian product. If these tuples, as in the case of arrays, are all taken from the same set, you're going to call them a power set. And when I say canonical language, right, what it means is that logicians that have studied these power sets, these product sets, they normally use component-wise operations. So operations that roughly lift or operations or relations, right? So roughly, they lift a relation that holds in each of the components that I was showing in that grid to the array by just saying the relation in the array holds if and only if the relation holds in every component. Okay, so that's the language that logicians typically add to these sets. And the result then is this structure here that they call product structure or power structure. And the first realization of this paper was that combinatory array logic was essentially, okay, the same thing as data structure. And that wasn't pointed out before. And that's nice because there are many results in logic, in particular in model theory, that talk about data structure. So it's actually several logicians that have studied this. First, Mostowski, and later Pfefferman and Bott. And they characterize the decidability of the theory of the power structure, so the set of formulas that are true semantically under the power structure model. Now, there is a problem. And the problem is that their methods, their decision procedures for those theories, they generate exponentially many formulas. And so what you get at the end of the day is very high complexity. So what we did was basically, well, let's again go to the simplest case, which is the existential fragment. So we assume that our formula has an purely existential prefix. What happens now? We're out of the classical theory, so what we basically did was look at the literature, and in the literature we had two hints. One came from the original paper of combinatory array logic, where it was stated that the existential fragment of a combinatory array logic is in NP. Now, the problem is that in that paper there are a lot of, well, it depends, but for a non-expert in SMT solvers, there are a lot of considerations about the SMT solver structure, and this particular statement is not proof explicitly. So basically they say, follows by a similar argument as the previous development, which is just a quantifier-free array theory. So in essence, it was difficult to generalize from that fragment to what we wanted, right? So, and then there was a second thing, which would be implied by that result, which was essentially something called Skolem arithmetic. And the existential fragment of that arithmetic was studied in Eric Gredel's PhD thesis. And he basically proved that it was in NP, okay? Now, we were interested in that particular theory because it's the weak direct power of Pressburger arithmetic. And again, it wasn't clear how to generalize, okay, that proof, because it seemed specific to the arithmetic theories involved. So we had to come up with our own proof, and in fact, it's super simple. Here's the statement we want to show. We want to show that if we assume that the existential fragment of the theory of the model is in NP, of the component model is in NP, then the existential theory of the array model that we are considering is also in NP. And so first thing is to say, well, since we are in NP, we can always guess one disjunct of the DNF form, because its size will be linear in terms of the size of the original formula. And once we write this disjunct, we just apply the semantics of power structure. So positive relations just say that, so Ri, okay, Ri has to hold in every component. And the negation just says there exists some component where not Rj has to hold. So to make things simpler, and that's in fact the way we started to prove it, let's assume that the index set I is infinite. So then one could simply say, since I have a finite number of negative relations, I can just guess, I can just say, well, let's take some index with, of course, the positive relations and one negative relation. Then we take another, we take as much as we want because we have infinite number of them. And so that leads somehow to this picture where you have Ri holding in every component, and forget about this guy by now. You get negative relations in some of the components. And the nice thing, and the key idea that also generalizes, is that these guys you can assume they all have the same solution. So essentially what you do is you query the NP procedure for the component theory, and you get solutions for these finitely and linearly many components, and then you just do another query for the purely positive component. And so you can simply replicate that solution. And then, well, the case where I is not infinite, it then just follows by guessing a particular partition of the negative relations. So that was the proof, and well, let's see what we are missing. So what we are missing is, because we have a complexity result, we have somehow, let's see, we are missing, I can say what we're missing. So we are missing an improvement in the properties that we capture, okay, and that's gonna be cardinalities. we have a nice theoretical foundation, and then we have a complexity result, but we need some generalization. The first observation is that, well, this result is completely agnostic to the component theory and to the index set. So that means I can iterate. So if I start with a component theory here, it's in NP, well, then the array theory is also in NP, and then, in fact, I can get two multidimensional arrays. OK, that's nice. The second observation is that, and that's going to be the main generalization, and you could think of it as a main contribution, is, well, we also can have cardinality constraints saying, number of relations, number of indices where some local property to that index, to that component holds. And then the last part of the paper just says, well, if we have cardinalities, we can encode these functions and this basically equality relation when you have an array right, because, well, we just can say the number of positions where the array is going to be equal to the updated value, well, it just contains the index where we are updating, things like that. So let's focus in the main contribution. And the first motivation would be why cardinalities? The answer is cardinalities arise in our proof pretty easily, right? Because positive relations basically made all our indices, the points here, right, stay within a certain region of the Venn diagram. So here I'm assuming that the basic circles of your Venn diagram, they are a set of indices that satisfy some relation. And then negative relations just tell you that certain subregions of that main region have at least one index. Okay, so that's very basic cardinality operations, so let's generalize. And to generalize, we use the one language for that purpose. It's called quantifier-free Boolean algebra and Pressburger arithmetic, so QF-BAPA in short. Okay. And let's see why, if we add QF-BAPA to that language, we still remain in NP. And the reason is basically, well, we use this result from 2007 of Kunc and Rinard, which is in turn based on this result by S. Dan and Esmonin. So here's the rough idea. Let's say I have a, well, this is the kind of formula that we handle, okay? F is going to be QF-BAPA formula. And the sets, well, they are just a set of indices where some local property holds. Now, so imagine this formula is satisfiable. We'll see how we can check that, right? If it's satisfiable, we roughly have a picture like this with this filled out. And then we can map it into the Venn regions. And here the Venn regions are maybe easily to see, so they are just these sets, okay? Set of indices such that whatever holds. So because it's satisfiable, this formula we assume is satisfiable, then F will be satisfiable, okay? And because of the result of Kunc and Rinard, what we know is that from the set of regions that were occupied by our indices, we can extract a polynomial number of them, which are in blue here, okay? Now, and here comes the idea from the basic proof. Basically, one could say, well, we still need, okay, so what Kunc and Rinard tells you is that that solution translates to some other solution in these blue regions. And the basic idea to finish the proof is to say, well, these blue regions were inhabited because I selected it from regions that were already, for some index here, there was somebody here. So that means the underlying formula is going to be true. So I can simply, I don't have to remember like 4 or 2 indices. No, it suffices with 1. And we do exactly the same as before. We just get this one and replicate it as many times as the cardinality constraints impose. So I hope that I have conveyed some idea of why the NP argument also works in this setting. Now, the final thing would be to convince you that there are more extensions to do, right? And the first extension, I would say, is more or less immediate. Is instead of cardinalities, let's have a probability operator, also rational numbers. That shouldn't be very hard. The second basic extension has to do with automata, because, as I said, the theoretical foundations of array fragments are normally go through automata, and there are connections to these product structures, okay, an automata, namely some papers of Alexis Bess in model theory. But again, the problem is that they are made for the decidable case. So maybe for this case, some other arguments are needed. And finally, one could always try harder specifications and also compare to other existing fragments. So for a summary of the contributions, we basically argued the importance, right, of having efficient decision procedures for arrays. Our goal was always to remain within NP. And in doing so, we basically demonstrated how one would use model theoretic methods to that end, to classify. Basically, we classified two known fragments, the one of combinatory array logic, and I forgot to say, but another fragment by Alberti, Ghilardi, and Pagani that also treated cardinality constraints, but in a more limited approach. And anyways, we demonstrated how these model theoretic methods contribute to classify and discover new decidable fragments. And in doing so, we offered the steps to having a better understanding of the logical and computational properties of array theories. So that was all from my side, and I'm happy to take any questions you may have. And now, I should disconnect myself.
Okay, thanks, Rodrigo. Yeah, are there any questions in the live audience?
Maybe one quick question. So the combinatory array logic can encode the theory of sets, if I remember correctly. So does this give you a different Baba reduction? Or is it that you, in the end, anyway, reduce back to Baba in your proof?
So could you repeat the first part? It gives combinatory array logic has...
yeah, you can encode the theory of sets.
Okay.
And so does this give you a different kind of reduction for Baba?
Yeah, I also thought about this part. It has sets on it, they show that. But yeah, I believe this should be different because I mean, at the time when they encode sets in terms of combinatory array logic, right? So, while this here encodes basically combinatory array logic in terms of other things. Well, I haven't thought thoroughly about that, but yeah, there's some duplication to my. I think so. Yeah.
Thank you.
So, Rodrigo?
Yeah.
Yeah, so can you characterize the kind of array theory extensions that keep you in NP, and which ones actually take you beyond NP?
So yeah, that would be very nice. And I hadn't any tool to do that until I believe recently. So it's not something that I've seen done anywhere, right? To characterize what you can do in NP or you can't. And so I don't have a definite answer to that, but the good path might be to study more closely not Pfefferman-Bott theorem, which is what we've done, but Mostowski's work, because he was a previous work. He concentrated on power structures, and he studies definability issues too, right? So it's more complete account. But yeah, I think characterizing completely in MP may be hard, because if you look at what we did also, right, it's a very simple model, right? While so it's basically these tuples, right, and they are very well understood. Now there should be other variations of theories of arrays that probably cannot be encoded here. So yeah, it's a very hard question, I think. Yeah. I don't know if that answered somehow what you.
Okay, yeah, I agree. It is a hard question there, but even if you can characterize it for certain operators, and you can show that certain classes of operators are actually
yeah, well,
keep you within NP.
Yeah. So there is some discussion of that also, so having some classes of operators in not in the paper of combinatorial array logic, but in a technical report that they published, and they studied, because they call it combinatorial array logic, right? And it maps to theory of combinators. So there they studied variations like adding identity operator, right? And I believe S combinator or K, they have, so S combinator. And they showed there that the resulting fragment was undecidable. So yeah, at least for those we know, right, that wouldn't work. It's not non-trivial to have low complexity fragments here. Yeah.
Okay, any other questions?
I don't think we have anything here.